we have been talking about reflection and transmission of electromagnetic wave across a planar boundary. In particular, we have talked about plane waves when they are normally incident or obliquely incident, and we came up with how much amplitude is reflected. So, what we have covered is oblique incidence of an EM wave, and we are talking about plane waves on a planar boundary. And we have derived E reflected, E transmitted in terms of E incident, and from that we can get the reflection coefficient and the transmission coefficient and so on, which we will be talking about in this lecture. So, in this lecture we will talk about the transmission and reflection coefficients for oblique incidence, and this will also take us to the Brewster angle, polarization by reflection, and the total internal reflection, and so on. I just wanted to emphasize that I talked about materials that are non-permeable or non-magnetic, so that the expressions are simplified. If you want to include these, this is very easy to do, but I want to focus on really what is happening in physics, so it does not really limit us in that. So, to begin with, let me just remind you, we considered two possibilities. If there was a plane electromagnetic wave coming in with polarization in the plane of the incidence, P polarization, and then we also talked about S polarization, where the electric field is perpendicular to the incidence plane. This was known as S polarization. And when we considered non-magnetic medium, formula become very simple. Then E R amplitude divided by E I 0 was tangent of theta incident minus theta transmission over tangent of theta incident plus theta transmission. I had a negative sign in front here, and for S polarization, E reflected 0 by E incident was equal to sine of theta transmission theta I over sine of theta t plus theta I. If you are following the notation in Jackson, you will see that in P polarization, the sign obtained in these lectures is different from that in Jackson. This should not bother you, because what we did in these lectures is, when I took this wave reflected, the E field that I took for the reflected wave was like shown in the figure. This is our notes. What Jackson does is that the E field gets rotated with the reflected wave. So, the sign I obtained is different from his by a minus sign, right? Rest of the expressions are the same. And again, I remind you, in this case, what we have done is taken mu 1 to be equal to mu 2 to be equal to mu 0. So, non-magnetic materials. Generalizing is very easy. All you get is a ratio of mu 1 and mu 2 also thrown in somewhere. But this is very easy to remember, and that is why I am emphasizing on this, and we do not really lose any physics. We will get all the physics out of these formula. And also, the refractive index therefore comes out to be square root of epsilon relative. Let us now translate these expressions to those in terms of n and incident angles and things like those. So, for P polarization, I have E r 0 over E I 0 equals tangent of theta t minus theta I divided by tangent of theta t plus theta I, which I can write as sine of theta t minus theta I times cosine of theta t plus theta I divided by cosine of theta t minus theta I and sine of theta t plus theta I. Expand these and you get sine theta t cosine theta I minus cosine theta t sine theta I times cosine theta t cosine theta I minus sine theta t sine theta I divided by all plus signs. This then is equal to cosine square theta I sine theta t cosine of theta t minus sine square theta t sine theta I cosine theta I. I am actually going the other way from the derivation that I did last time, minus cosine square theta t sine theta I cosine theta I plus sine square theta t plus sine square theta I cosine theta t sine theta t divided by all plus signs. Now, this, as I said, going back what I did last time. So, this is actually nothing but sine theta t cosine theta t minus sine theta I cosine theta I divided by the plus sign sine theta t cosine theta t plus sine theta I cosine theta I. I am going through this exercise so that you see how things are evolving. All right. So, I am just, last time we went from what I have written now to the expression I wrote at the top of this slide, right, and I write that expression because that is very easy to remember. Now, let us substitute. I know that sine theta t is equal to sine theta I over n, and therefore, cosine of theta t is equal to square root of 1 minus sine square theta t, which is sine square theta I divided by n square. And let me substitute that in. So, I get E r 0 over E I 0 is equal to sine theta I divided by n times the square root of 1 minus sine square theta I divided by n square minus sine theta I cosine of theta I divided by everything with plus. So, sine theta I divided by n square root of 1 minus sine square theta I divided by n square plus sine theta I cosine of theta I. Sine theta I cancels, and I can simplify this expression to square root of n square minus sine square theta I minus n cosine theta I divided by square root of n square minus sine square theta I plus n cosine of theta I. That is the ratio. Jackson gives n cosine of theta I minus square root of n square minus sine square theta I divided by everything with plus n cosine theta I plus square root of n square minus sine square theta I. So, that sign differs because we have taken the direction of electromagnetic field to be different. So, let us now calculate the reflection coefficient for p polarized light. So, what is happening is this wave is coming in and gets reflected. It has two components, component going up and component going perpendicular to the plane, and it is this component that takes the energy across. So, in our case, we will be talking about how much energy is coming in and how much energy is going out. So, energy is nothing but Poynting vector, and I am talking about its x component, time averaged, reflected, divided by Poynting vector dot x incident. By the way, in all this, you should keep in mind that we are working in complex notation. Here it does not matter, but when I talk about total internal reflection and all that, it does matter. So, finally, actually what I am taking is the real quantity, right, and I have done one lecture on how we use complex notation in harmonic waves, and that is what I am using here. And this comes because we have been making use of e raised to I k x minus omega t at the boundary. So, I am using this notation, which makes life easy, but I have to be careful that I take magnitude squares, I take E star, BV star and so on. I will urge you to go back to that lecture and see what is happening. So, now in this case, if I am talking about the ratio of reflected intensity divided by incident intensity. Now, remember this S is nothing but 1/2 V epsilon mod E square. Right, this comes from that 1/mu0 E cross B star divided by 2. This is what we had derived earlier, or which is equivalent to real part of E cross B over mu0 time averaged. It is all the same. Now, in our case, since reflected and incident lights both are in the same medium, V is the same, V and epsilon is also the same. So, all you get is that the ratio, which is the reflectance, comes out to be mod E square ratios, and that will be root n square minus sin square theta I minus cosine of theta I divided by mod n square minus sin square theta I plus cosine of theta I whole square. That is the reflectance, and then you can plot it as a function of theta I. So, if theta I goes to 0, then reflectance becomes 1/1. Reflectance becomes, then reflectance becomes n minus 1 divided by n plus 1 whole square. And if theta I goes to pi by 2, then reflectance becomes n over n, which is 1. So, in the previous case, light is falling normally. In the second case, it is at grazing angle. So, at very low angle from the surface, reflectance is very high, and at normal it is what it is. Keep in mind that if I could also treat through this, if the two sides are n1 and n2, then n actually refers to n2 over n1. It is a relative refractive index of one medium with respect to the other. From this, you can calculate the transmission coefficient T, which is 1 minus r. You could also calculate it by using E transmitted and the corresponding Poynting vectors. So, let me just indicate how would you do it. When this wave is coming in, it is getting reflected and it is also getting transmitted. Then if I were to calculate transmittance, it would be 1/2 V in medium 2 epsilon in medium 2 mod E t square divided by 1/2 speed in medium 1 epsilon 1 mod E I square, and this would give me V 2 epsilon 2 over V 1 epsilon 1 mod E t over E I square, which I could also write as epsilon 2 is nothing but n 2 square. So, it will be n 2 divided by n 1 E t over E I square, and this should also come out to be 1 minus r. So, either I can calculate by calculating r and subtract from 1, or I could do an explicit calculation. The second thing you notice about this formula that we have written is polarization by reflection. So, I have written the formula as E r 0 over E I 0, which is the ratio of the amplitudes tangent of theta t minus theta I divided by tangent of theta t plus theta I, which is also equal to, you just calculated, square root of n square minus sin square theta I minus cosine of theta I divided by square root of n square minus sin square theta I plus cosine of theta I. So, whenever theta t plus theta I is pi by 2, E r 0 is 0. You could also calculate it by writing n square minus sin square theta I is equal to cosine square, there is an n somewhere, I think I missed that, let us see, there is an n here, please correct this in the previous slide also, correction. So, if n square minus sin square theta I is equal to n square cosine square theta I, then also you would have the same condition, which is equivalent to the condition that I just wrote, and this gives you tangent of theta I is equal to n, and this is known as this angle is known as Brewster's angle. If the electromagnetic wave is falling at an angle theta I, which is tan inverse n, or tan inverse the relative refractive index, the reflected wave would have no p polarization. It will be polarized in the s direction. Right? So, this is one way of creating polarization. So, what one is saying is, if I have this medium and ray is falling at this theta Brewster's, then the reflected ray has only S polarization, and theta I plus theta t is equal to 90 degrees. This way one can create polarized light. This also implies all reflected light will be partially polarized, and this gives you an opportunity to cut one kind of polarization or the other using polarization filters. Those who do photography or do some playing with optics instruments, you know what polarizer filters are. By rotating them, you can cut down the intensity, background intensity versus the reflected light intensity. That can be adjusted using these. Let us now look at S polarization. S polarization says that E r 0 over E I 0 is sin theta t minus theta I divided by sin theta t plus theta I, and again you work it out and you end up getting cosine of theta I minus the square root of n square minus sin square theta I divided by cosine of theta I plus square root of n square minus sin square theta I. That is the answer. Now, in both cases you see for theta I going to 0, we recover the normal as it should be. I want to give you a problem here. Plot reflection and transmission as a function of theta I for both S and P polarization. Next, I want to deal with the phenomena of total internal reflection. You see, for both P and S, we had E R 0 over E I 0. I had n cosine theta I, n cosine theta I, minus the square root of n square minus sine square theta I, plus the square root of n square minus sine square theta I. This is for P, and for S polarization, I had cosine of theta I minus the square root of n square minus sine square theta I divided by cosine theta I minus square root of n square minus sine square theta I. So this one is for S polarization, and the other one is for P polarization. Both have this term square root of n square minus sine square theta I. So, if n is less than 1, right, that means the wave is going from a medium with higher refractive index that with lower refractive index. In that case, n square minus sine square theta I square root will be imaginary if sine theta I is greater than n, or theta I is greater than sine inverse n. Right? What you have learned it earlier in optics is that there is a critical angle where theta transmission becomes pi by 2, and therefore, sine theta I over sine theta t becomes sine theta I, and this is equal to 1 over n, and this is equal to the refractive index of the second medium divided by refractive index of the first medium, which is n relative. So, theta I is sine inverse n, and in this case n happens to be less than 1. So, both are consistent. What is happening is, beyond the critical angle, n square minus sine square theta I is becoming imaginary. What does that mean? So, I have this electromagnetic wave coming in, and this is at an angle theta I, which is greater than the refractive index. In that case, I have sine theta I greater than n. Now, notice the transmitted wave has a k, which is equal to omega over v, which is equal to n omega over c, or in this case n is less than 1, n relative. So, we will just leave it here, n over v. Right. Now, this has two components. It has a component in the x direction and the other component, let us say this is y direction. So, k cosine of theta t, which is equal to k square root of 1 minus sine square theta I divided by n square, will become imaginary. And that means, when I write the transmitted wave, this is going to be E t 0 e raised to I k x x plus k y y minus omega t. K x is purely imaginary, and therefore, you end up getting this as e t 0 e raised to minus whatever that k x mod is x e raised to I k y y minus omega t. So, if you look at the amplitude in the x direction, it is decaying exponentially, and there is no propagation in the x direction. The wave travels in the y direction. So, there is no transfer of energy across. So, what is happening in this case? So, suppose I have a system with n 1 here, n 2 here, a wave comes in with sin theta I, which is equal to n 2 over n 1, or theta I greater than sin inverse n 2 over n 1, then there is going to be a wave on the other side, which is traveling only in the perpendicular, only in the parallel direction, and this way the amplitude is decaying. So, all the energy flow is in this direction, shown by red. This is known as evanescent wave. It transports no energy across the surface. So, in this case, there is no transport of energy across the surface. All energy is reflected. This you can see very easily, because E r over E I is either with this n cosine theta I minus purely imaginary number I times some number divided by n cosine theta I plus purely imaginary number, and for the s it is without the n, or cosine theta I minus I purely imaginary number divided by cosine of theta I plus I imaginary number. So, mod of E r over E I is 1, and this means all the energy is reflected. You can also see it through transmission coefficient. The transmission coefficient is nothing but S dot x transmitted divided by S dot x incident. Now, in this case, the k transmitted is nothing but I k x plus k y. And remember, what is S? S is in the direction of k transmitted. If I take real part, or there should be a real part also, real part of S dot x, this will come out to be proportional to I mod k x real part, and that is 0. So, this also indicates there is no transmission. So, if I have this medium n 1 greater than n 2, and this is falling at an angle greater than critical angle, then you have this wave propagating this way. However, there is this amplitude. The field exists here up to a distance of the order of 1 over mod k x. So, if I take another medium of say the same refractive index n 1, this is n 2, such that the thickness here d is less than 1 over mod k x. In that case, the other boundary will also feel some field out here, and the wave will start getting transmitted. So, what will happen in this case is the wave comes in, and then it will get transmitted across some small amplitude, and that is because there is field there, and this is purely a wave phenomena. Let me just discuss this a little more in the next slide. So, what we are saying is, during the total internal reflection, on the surface on the other side this field exists, but the amplitude keeps going down exponentially. However, if I bring another surface in between, this surface feels this field and then the wave will go through. If this is n1, this is n1, this is n2, the wave will propagate again with the same k. This is related to wave nature. Whenever there is a wave, amplitude suddenly does not go to 0. So, amplitude does not go to 0 all of a sudden, but decays. So, if you can feel the field on the other side, it will again transmit, and this is quantum mechanically related to phenomena of tunneling. Because electrons or particles have a wave associated with them. So, if they are incident somewhere, this wave does not go to 0, the amplitude does not go to 0 right away, it decays exponentially, right. You know that e raised to minus the square root of some mod E x. And then if I bring another medium here, that is, if I have a different potential where the electron can again propagate, then the electron goes through. Here the refractive index in quantum mechanical phenomena is actually given by different potentials. So, if I have different potentials and electron coming with energy less than the potential barrier, it can tunnel through. So, total internal reflection in electromagnetic wave is also related to tunneling phenomena. After looking at this way, you should not be surprised that tunneling takes place, because wherever there are waves, they will do this, right. So, I just wanted to point that out. So, let me conclude this lecture by saying that we, for reflectance and only in bracket transmittance of plane EM wave incident obliquely on a planar dielectric boundary, and we discussed Brewster's angle, and this leads to polarization by reflection, and we also discussed phenomena of total internal reflection, and this is related to waves, and then therefore, this is also related to tunneling in quantum mechanics. So, if you really master these, oblique, incident, wave, and how they reflect and how they transmit, these all are good skills that you will develop, that you can then take over to quantum mechanics also. So, I hope you will work out these things, whatever I am leaving out. I have given you an indication how to do it. You can always fill in the details like mu, mu prime, mu 1, mu 2, and so on, which I would expect you to do with time. Thank you.